In this video, I want to talk about deriving a formula for the singular value decomposition. So I'm going to let A be an m by n matrix. So it's not necessarily square, and it's definitely not necessarily going to be a symmetric matrix. So our goal, remember from the last video, is we want to write A in the following form. A is equal to U times sigma times V transpose, where U is an m by m orthogonal matrix, V is an n by n orthogonal matrix, and sigma is a matrix that's almost diagonal, although it's not necessarily square. It's going to be the same size as A, so m by n. But just like a diagonal matrix, the only entries in it that are allowed to be non-zero have to be along the main diagonal. Okay, so one of the challenges behind trying to do this, especially when we compare this to what we talked about with symmetric matrices, was with symmetric matrices, they were automatically orthogonally diagonalizable. And that was nice. But A right now is not necessarily a symmetric matrix. So what I'm going to do is I'm going to form a symmetric matrix that's related to A. So notice that A transpose times A is symmetric. So you should verify this. It's actually pretty quick to verify, but you should verify this. So we are actually happy that this is symmetric. So to verify this, the type of thing that you'd want to do is you'd want to sort of check is, when you transpose this, is A transpose A, that whole thing transposed, is that equal to that matrix? Is that equal to A transpose times A? So definitely pause the video and just check this. It should be pretty quick. All right, so because this matrix is symmetric, that means this matrix, A transpose A, is definitely orthogonally diagonalizable. So a matrix is orthogonally diagonalizable if and only if it's symmetric. So we saw this in section 7.1. This was called the Spectral Theorem back in 7.1. It's not super important that we know what it was called, as long as we just know this fact that if my matrix is symmetric, it is orthogonally diagonalizable. So one of the things that meant was it's diagonalizable, so we can find a basis of eigenvectors. And moreover, not only can we do that, we can find an orthonormal basis of eigenvectors. So A transpose A has an orthonormal basis of eigenvectors. So I'll call those V1, comma, dot, 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 up to Vn. So if it has these eigenvectors, it'll have corresponding eigenvalues. So let me say that the corresponding eigenvalues for these eigenvectors, let's call them lambda 1, comma, dot, 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 up to lambda n. And some of these eigenvalues might be repeating. All right. So one of the reasons why this is going to be useful to us is it turns out that these eigenvectors, V1 up to Vn, are going to be the columns of the matrix V in our singular value decomposition. So that is a key fact, and we will prove this soon. All right, so these eigenvectors, V1 up to Vn, they're eigenvectors of A transpose A. But we're trying to find a singular value decomposition for the matrix A, not for A transpose times A. So next I want to talk about how do we connect these eigenvectors, V1 up to Vn, to A. All right, so what can we do? What can we do to connect them? So because they're eigenvectors, I know that if we write something like A transpose times A, that's my matrix, that they're the eigenvectors of, times Vi, so one of these eigenvectors, well, that should be equal to its corresponding eigenvalue, lambda I, times that eigenvector, Vi. So this should be true for all values of I here in between 1 and n. All right. So when we look at this left-hand side, A transpose A times VI, we've seen things that look like this before. This is almost a dot product. To be a dot product, it would have to look like some vector transposed times some other vector. Like if I had U transpose times V, that's the same thing as U dotted with V. So it's almost a dot product over there. What I need to do is, it's sort of missing something. It's missing sort of a vector being transposed here. So in particular, what I want to include there is I want to have VI transpose. So what I'll do is I'll just multiply both sides by VI transpose on the left. And we've seen that before. We've seen this technique before, where we multiply both sides by something like VI transpose on the left. So we get that times A transpose times A times VI, and then this is, we got a lambda I VI on the right side. So now we can rewrite what we have on the left as A times VI transpose. So the first two terms can be rewritten like this, and then times A times VI. Lambda is a constant, so we can move that to the front. Lambda I times VI transpose times VI. Now we can rewrite these things as dot products. So we have A times VI dotted with itself, so dotted with A times VI. And then over here on the right, we have lambda I times VI dotted with itself. All right, so when you have a vector dotted with itself like this, that's the length of that vector squared. So it's the length of VI squared. But the length of VI squared is actually 1, since we took the VI's to be orthonormal, since the VI's are orthonormal. Okay, so if we rewrite the left-hand side as a length, that'll be the length of A times VI squared. Let's write that squared a little bit better. Squared. And on the right-hand side, this equals lambda I. So the length of A times VI squared equals lambda I. So this gives us a relationship between A, the eigenvectors of A transpose A, those are the VI's, and these eigenvalues, and it relates it to lengths. The other key thing that this tells us is, so now we know that lambda I is something squared. So that means that lambda I must be greater than or equal to 0 for all I. So we're assuming here that we're working with purely real numbers. We're going, just working purely with real numbers. That's why I can say that lambda I is definitely going to be greater than or equal to 0. So what I want to do next is, now I know all the eigenvalues are real, and in fact they're all non-negative. I'm going to reorder them in what's called descending order. So reorder the eigenvalues of my matrix A transpose A, so that lambda 1 is going to be the biggest, lambda 2 is the second biggest, all the way up until lambda n is going to be the smallest. But we know that all of these are greater than or equal to 0. And of course, some of these eigenvalues might be the same. They might be repeats. All right, so what I want to do now is I want to define what's called a singular value. So when we take the square root of these eigenvalues, of these lambda i's, that is what the singular values are. So the notation for singular values is we write this is the Greek lowercase sigma. So we say sigma I is the square root of lambda I. So these sigma i's are called the singular values of A. And notice that the way that the singular values are ordered matches how their corresponding eigenvalues are ordered. So sigma 1 is the largest singular value, and sigma n is the smallest singular value. So the singular values of A correspond to the eigenvalues of A transpose A. So not to the eigenvalues of A, but to the eigenvalues of A transpose A. All right, so with this new definition in mind, we are ready to state an important fact that ties back to the statement that we had here. So we know that the length of A times VI squared equals lambda I. But now, according to our definition of singular values, lambda I is sigma I squared. And if we square root both sides of this, we will get that the length of A times VI equals sigma I. I don't need to worry about putting a plus or minus when I square root this, because neither one of these things, either the length of AVI or the singular value sigma I, can be negative. All right, and the key fact that we want to keep in mind is it will turn out that the singular values, so these sigma i's, are going to be the entries that are on the main diagonal of the matrix capital sigma in the singular value decomposition. A equals U times sigma times V transpose. So we'll prove this later in the video. So at this point, we have stated a fact for what the columns of V are, as well as a key fact for what the entries of sigma are. So what's left to be done is to state something about what U looks like. So that'll come a little bit later in this video as well. So next, I want to state a key theorem that'll connect to what U looks like. So here is the theorem. It says that if sigma 1 up to sigma r are all, and actually I miswrote something here. This should just say greater than 0, not greater than or equal to. So if sigma 1 up to sigma r are all greater than 0, and sigma r plus 1 up until sigma n all equal 0, so this is saying that my matrix A has r non-zero singular values. Then it'll turn out that A times V1 all the way up until A times VR is an orthogonal basis for the column space of A. And moreover, the rank of my matrix will be R. So in this theorem statement, the V's are the eigenvectors of A transpose A. I'm using the same sort of framework that we've established in the video up until this point. Okay, so we need to show that this set A times V1 up until A times VR is an orthogonal basis. To do that, there are two things that we need to show. Pause the video for about 1 minute and see if you can identify just what are the two things that we need to show. Don't worry about trying to show them in the minute. It won't be enough time, I think, to show them. But just see if you can identify what are the two things that we would need to show that this set is an orthogonal basis for the column space of A. So 4, 3, 2, 1, pause the video. Pause the video for about a minute and see if you can identify what those two things are we need to establish. All right, so hopefully you've done that. Hopefully you've paused the video and thought about this for about a minute. So there are two things that we need to show. We need to show that it's orthogonal, and we need to show it's a basis. So we just need to break down those two words a little bit. So first, we need to show that this set of vectors is an orthogonal set. And then second, we need to show that it's a basis. It's a basis for what? For the column space of A. So to show something is an orthogonal set, we just have to show that when you take the dot product of two different elements in that set, it's going to be 0 always. And to show something as a basis, let's break it down a little bit more. So to show something as basis, we need to show two things. We need to show that it's linearly independent. So our set of vectors needs to be linearly independent. And the second thing that we need is we need this set to span whatever vector space we're talking about. In this case, the column space of A. We need it to span, in our problem, the column space of A. All right, so let's first establish one. Let's show that this is an orthogonal set. All right, so So the first thing that we're going to do to show that it's orthogonal is we'll take the dot product of two different elements of the set. So I want to take AVI dotted with AVJ for I is not equal to j. So that condition that I is not equal to j means we're dot producting two different vectors in this set. Okay, so now let's rewrite this. So this becomes A times VI transpose times A times VJ. And now I can use a property of the transpose to rewrite these first two terms as VI transpose times A transpose, and then times A times VJ. And in fact, maybe I want to simplify A times VJ. Do I want to simplify that? So actually, I can't just simplify A times VJ, but I can simplify this whole thing, A transpose A times VJ. Because remember, VJ is an eigenvector of not just A. Let me just say it this way. It's not an eigenvector of A. It's an eigenvector of A transpose A. So this is an eigenvector of A transpose A with eigenvalue lambda j. So using that fact, we have VI transpose at the front, and then this will be multiplied by lambda j times that eigenvector Vj. And then lambda j is a constant, so we can move that to the front. So we get, lambda j coming to the front, multiplying Vi transpose times Vj, which will be Vi dotted with Vj. And we know what Vi dotted with Vj is. So over here, we already know that the Vi's are orthogonal. In fact, we know that they're orthonormal. Let's actually state that. They are actually orthonormal. Orthonormal. So we know that dot product is going to be 0. So overall, we have that this whole thing is 0. So this shows that AVI, and AVJ are orthogonal for all I not equal to j. So we've shown that our set of vectors is orthogonal. All right, so the next thing that we need to do is show that our set is a basis for a column space of A. So we need to check that it's linearly independent, and we need to show that it spans the column space of A. So let's start with linear independence. So for the linear independence portion, I've written most of the argument out. I just want to fill in the blanks together. Okay, so we've seen before that the length of A times Vi is equal to sigma I for all vectors, for all I. So we saw that on the previous page. We had it here. The length of A times Vi equaled sigma I. We got that after we did this computation involving the eigenvalues and eigenvectors of A transpose A, and after we defined our singular values. Okay, so we know that the length of AVI is equal to sigma I for all I. So one of the things that tells us in particular is that A times Vi would be equal to the 0 vector if and only if sigma I was equal to 0. So the only way for the length here on the left to be 0 is if sigma I was 0. So what that means is for I in between 1 and r, those are the values that corresponded to the non-zero singular values. So for those values of I, sigma I is greater than 0. It is non-zero. So it is non-zero when I is in between 1 to r. And if sigma I is non-zero, that definitely means that A times Vi is not 0. So at this point, we know that our set of vectors, AV1 up until AVR. We've already shown that this is an orthogonal set because we did that up above. And now we know it's also a set of non-zero vectors. And we've established a theorem back in chapter 6 that said if we have an orthogonal set of non-zero vectors, it is definitely linearly independent. So that shows linear independence. So we've shown linear independence, we've shown orthogonality. Okay, what's left to do is show the spanning portion. All right, so we got to show that our set of vectors spans the column space of A. All right, so to do that, to show that it spans the column space of A, let's begin by letting Y be an element of the column space of A. So I need to show that we can write Y as a linear combination of AV1 up until AVR. Because since Y is arbitrary, if we can show that we can write Y as a linear combination of AV1 up until AVR, that'll actually show that we can write anything that's in the column space as a linear combination of AV1 up until AVR. And that's what we need, because that would mean that the set of vectors spans the column space of A. In other words, we could write anything in the column space of A as a linear combination of these vectors. All right, so let's break this down. If Y is in the column space of A, then this means that Y equals A times X for some vector X that's in Rn. In other words, for Y to be in the column space of A, it's in the range of the associated linear transformation. That's why I can get Y out after I multiply A by some vector X. So since we know that V1 up to Vn is a basis for Rn, and now we know that X is in Rn, that means we can write X as a linear combination of V1 up to Vn. So C1 V1 plus dot 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 plus Cn Vn. All right, so next, let's write the fact that Y equals A times X, and now plug in X into this. So I'm going to plug this whole thing in for the X and distribute the A. If we do that, we'll get C1 times A times V1 plus dot dot dot. Eventually I'll get to CR times A times VR. After that, we'll have CR plus 1 times A times VR plus 1, and then plus dot 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 plus, eventually I'll get to CN times A times Vn. Alrighty. So the reason I'm sort of splitting this up in terms of the first R terms and then everything after those first R terms is because of what we observed earlier. So we observed earlier that the length of A times Vi is equal to sigma I, and moreover, the only way A times Vi is going to be equal to 0 is if and only if sigma I is 0. So I want to apply this down here. Let's apply this to our column space A portion. Okay, so if we apply this to our argument here, let me give myself a little bit of room to write here. So in this proof, sigma I equals 0 for I greater than R. Because in this proof, we're saying that there are non-zero singular values. And those have to be the first R because the singular values are ordered in descending order. They go from biggest to smallest. So after those first R non-zero singular values, all of the other sigma I's have to be 0. Okay, so one of the things that this will tell us is that A times Vi will be equal to 0 for I greater than R. Because we set up here that sigma I equals 0 if and only if A times Vi equals 0. Alright. Ooh. Oh, that shifted for some reason there. Ah, again. I don't know why it's shifting. Okay. All right, now there we go. All right, so I just want to bubble this. Okay, so what that'll let me do is that'll let me say that this is 0 all the way up to a times vn is 0. So everything after a times vr, all of those are going to be 0. So what we're left with is y is a linear combination of av1 up to avr. In other words, y is in the span of av1 comma up until avr. Okay, and because y was arbitrary, that means anything in the column space is in the span of these vectors. Or stating that another way, we've just shown that av1 up to avr spans the column space of A. Okay, so we've shown the spanning portion, and based off of what we showed above, this means that this set of vectors is an orthogonal basis. We showed orthogonality, we showed linear independence, which combined with the spanning property means it's a basis. It's an orthogonal basis for the column space of A. And the last part of the statement was to show that the rank is R. Well, at this point we have a basis, and we know that there are R elements in the basis. So that means the rank is R. So we've shown that AV1 up to AVR are an orthogonal basis for the column space of A. What I'm going to do next is I'm going to normalize them to get an orthonormal basis. So to normalize them, so I'm going to call the new set of basis vectors like the UIs. I'm going to let UI be AVI, but I have to normalize it. So I multiply it by 1 over its length. So 1 over the length of AVI. So what does this equal? This equals 1 over something, and then times AVI. But we know what AVI is. We had seen that earlier in the video. AVI, the length of AVI is equal to sigma I. So let's go ahead and plug that in. Got shifted over. Okay. Let's shift it back a little bit. So this denominator, the length of AVI, is sigma I. So we have 1 over sigma I times A times VI. And actually at this point, if we isolated for A times VI, and we move this sigma I over here, if we moved it over here, we'd get that A times VI equals sigma I times UI. So this is true for I in between 1 and R. Okay, so let me actually bubble this. So we end up with this equation that kind of looks similar to the form of an equation that we see with eigenvalues and eigenvectors, like AV equals lambda V. Not exactly the same though, because the sigma i's are a singular value, and the vectors that we have on the two sides are not the same vector. But still, it's similar to that. So when we prove our theorem about the singular value decomposition, which we're almost ready to state now, we're going to use a technique that's really similar to what we saw in proving the diagonalization theorem. So first, a key fact. So it'll turn out that these orthonormal vectors, these UIs, will be sum of the columns of the matrix U. And it's really important that I underline the word sum. There are situations where these UIs will be not all the columns of U, and we'll have to generate other ones, even after writing down what the UIs are. But that'll be perhaps the second example that I do. The first example that I do, that won't show up. All right, so we are ready to state the theorem now. So the singular value decomposition theorem. So this says that if A is a matrix m by n with rank R, we can write A in the form that we've been talking about, U times sigma times V transpose, where U and V are both orthogonal matrices. U is m by m, V is n by n. We've already said what the columns of V look like. They are eigenvectors of A transpose A. we've already said what sigma looks like. It's got this singular values. In this case, it's going to have R non-zero ones, because we're assuming the rank is R. The rank is R. So sigma 1 up to sigma R, these are the non-zero singular values. There might be other singular values that are 0, and those will extend sort of past this diagonal. They would sort of continue down further. And then everything else that's not in one of those spots is 0. So this matrix needs to be an m by n matrix. And if I look at just this portion in the upper left, this portion in the upper left is R by R. So let's write down the dimensions of each of these sort of sub-matrices that we have here. So for this 0 that we have to the right of that diagonal portion, it's also going to have R rows, but it's going to have n minus R columns. Okay, if I look at this 0 in the bottom left corner, that submatrix, so there are going to be m minus R rows, and there are going to be R columns. And then finally, if I go to the bottom right corner, this will have m minus R rows and n minus R columns. And we said what some of the columns of U are going to look like right before this. This was the key fact. All right, so let's prove this. Let's prove the singular value decomposition theorem. So, okay, so let's let A equal, actually no, let me word it like this. So we're trying to show that A equals U times sigma times V transpose. And that would be true if and only if. So if I multiply both sides by V on the right, we'd get AV equals sigma times, U times sigma. That's what we get if you multiply by V on the right. So recall that V transpose times V should be the identity, since V is an orthogonal matrix. Okay, so this is actually the form that we will show. So we will show this. So that's really similar to what we did in the diagonalization argument for the diagonalization theorem. We showed this type of form. All right, so what I'm going to do first is, no, I don't want to go that far down actually. We are going to take those U vectors and extend them to get a basis. So we're going to extend our set of vectors U1, up until UR. We know we have R of those vectors because the R matches up with the rank of our matrix. But this may not be enough to be a basis for Rm. So we're going to extend this to be, and we could do this to be an orthonormal basis. Extend this to be an orthonormal basis for Rn. So U1 up to UR, they are a set of linearly independent vectors. In fact, U1 up to UR are a set of orthonormal linearly independent vectors. But they're just not a basis for R. Did I say Rn? Yeah, I meant Rm there. So I wrote Rn, but I meant Rm here. Okay, yeah, so we want to extend these to be an orthonormal basis for Rm. So what that means is I need to add more vectors to this list to make it an orthonormal basis now. So I'm going to call those vectors UR plus 1, up until UM, and just put those as columns in a matrix. So that's going to be my matrix U. All right, so then let's look at A times V. So let's look at one of these sides. So A times V would be equal to, so it's going to be a matrix with AV1 as a column, up until AVR, and then I'll go to AVR plus 1, up until AVN. So in this matrix, these last columns after the rth column, these are all 0, since the length of A vi equals sigma I, and we know that sigma I equals 0 for I, just equals 0 for I greater than R. So the other key part to this is we can simplify the first few columns as well. Did we say it's above? Yeah, I think we did. So the other key fact is I'm going to use this statement right here. A times vi is equal to sigma I times ui. Okay, so that's going to be true here at the front. So A times vi is sigma I times, this is going to be sigma 1 times u1, sigma 1 u1. Up until AVR, this is going to be sigma R UR. So that's true up until VR. All right, so now writing down my matrix AV, we have sigma 1 U1, dot, 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 up until sigma R UR, and then a bunch of zeros after that, 0, dot, 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 0. All right, so that's A times V. Now let's do the other side. Let's do U times sigma. So U times sigma. So U has columns U1, dot, 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 up until UR, and then it's got UR plus 1, dot, 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 up until UM. Multiplying sigma, so sigma has the non-zero singular values, sigma 1 up to sigma n, in the sort of first diagonal area. And then it's got a bunch of submatrices that just all have zeros. All right, so when you multiply this matrix U times this matrix sigma, the first column will end up being sigma 1 U1, dot, 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 up until the rth column. Oops, I wrote sigma n here, but I should have been sigma r. Sigma r. The rth column will be sigma r times ur. And then all the columns after that will end up being 0. So zeros all beyond that. So that's what U times sigma is. U times sigma equals this. But notice that AV and U sigma are exactly the same. So at this point, we know that AV equals U sigma. So if you multiply both sides by V transpose on the right, we'll get what we wanted. You'll get A equals U sigma times V transpose. So that's because V times V transpose equals the identity, since V is an orthogonal matrix. And that is what we wanted to show. So we have proven this theorem. So there was a lot of theory in this video. In the next video, we will do an example.